When you observe the parameters of the k-means clustering estimator, you'll notice a parameter called training initial clusters. What does that mean and what does that indicate? In this demo, we'll see how you can perform k-means clustering using the TensorFlow library. All the code that I'm going to write is in the 2D arrays underscore k-means clustering.ipynb Python notebook. TensorFlow provides a built-in k-means clustering estimator, which means you don't have to actually write the code to iterate over the points and converge to the final cluster centroids. In this demo, we'll start off with simple two-dimensional data, that is points on an x and y axis, and see how we can apply clustering there. We'll move on to a more interesting example in the next demo. There is nothing interesting in the import statements. They are similar to the imports that we've seen so far in all of our TensorFlow demos, so I'm move on ahead. For this demo, I'm going to randomly generate the two-dimensional data on which we'll perform clustering. I'm going to do this using the random library from Python. This random.randint will generate a number between 1 and 1,000 because that's what I've specified here. Because I have a for statement as well, this will generate two numbers. Both of the numbers will be within this range. Two-dimensional data, so two numbers. The two numbers represent the x and y coordinates of this point. I'm going to go ahead and generate 100 such points. I'm going to generate random numbers in three different clumps. The first set of random numbers contain both of its coordinates in the range 1 to 1,000. The second set contain the coordinates in the range 700 to 2,000. And the third set contain coordinates in the range 1,700 to 3,000. So there are some natural clusters that I've already set up in this data. This is, of course, to just understand how k-means clustering works. When you see the data, and really just from seeing how I automatically generated, the clusters are kind of obvious. Take these individual arrays and put them all together so that all points are present in a single two-dimensional array. We'll go ahead and explore our data here. Here are 300 points in the coordinate space 1 to 3,000. The k-means clustering library is an estimator, which means it will require an input function to which we specify features and labels. Remember that clustering is an unsupervised learning technique. There are no labels associated with our input data, which means our input function will simply return the features in tensor form. All the points that we generated at random in two-dimensional space, we simply convert to a tensor. There are no labels and just return the tuple. I'll use the scatter plot from matplotlib in order to visualize this data. I want all the data to be in green, represented in the form of circles. If you look at the x and y axis of this scatter plot, you'll see the range of the coordinates that we've chosen ranges from 1 to around 3,000. That seems correct. This is our scatter plot. Because these data points have been generated artificially, you can see that there are some natural clusters within these groups. We generated data points from 1 to around 1,000. The second range was from 700 to around 2,000, and the third from 1,700 to around 3,000. You can see these clusters highlighted right here. Import the built-in TensorFlow library for k-means clustering. That is from tensorflow.contrib.learn.python.learn.estimators import k-means. In addition, we also import the clustering underscore ops library. This clustering underscore ops contains a number of enums that we use to specify hyperparameters for k-means clustering. Go ahead and instantiate the k-means clustering estimator, specify the hyperparameter, the number of clusters. Because we know that we've divided our data into three logical groups, we know that num clusters should be 3. Call estimator.fit to start the training process. We call this the training process even though there are no associated labels. The training process is simply to find the clusters in the X data. The argument to our training process is the input function, pass in the array that we just set up, and we train this for 1,000 steps. Once the training process is complete, you can call k-means estimator.clusters to get the cluster centers or the reference vectors for the clusters. And if you print it out to screen, notice that we get three points or three 2D points, which represents the cluster centers for the data that we passed in. All the points that we passed in had integer coordinates, but our cluster centers have floating point coordinates. It's not necessary for the centroids to be an actual point in our data set. Once again, let's use a scatter plot to visualize this. We'll plot the original data in green just like before. So we see how the data is scattered across the coordinate axis. In addition, we'll also plot the cluster centers in red. Here I've indicated that there are subplots within the main plot, one for the data and another for the cluster centers. And there you see it, our original data along with the cluster centers. Now this is very easy to visualize. You can really see k-means working here because our data was artificially generated to be in logical groups which were visible to us. When we set up this k-means estimator, we only specified the number of clusters. There are a number of other parameters that this model has, which took on default values. If you call k-means estimator.getParams, you can see what these other parameters are. One of these is a hyperparameter that we've discussed earlier. Here, the distance metric that we use to measure the distance between the centroid and any point within a cluster is the squared Euclidean distance. We can choose to use other distance metrics as well. One option that TensorFlow provides is the cosine distance. And as you can see, there are a number of other parameters here. I'll pick and choose some of the most important ones and explain to you what those are. I won't cover every parameter, I'll only cover the important ones here. One of the most important parameters is another hyperparameter, that is training initial clusters. This specifies how the cluster centroids were initialized before the k-means clustering algorithm began. The default is that the cluster centers are picked at random. You can also choose specific cluster centers, which you specify in the form of an array. You can also specify a function which generates these cluster centers, or you can use k-means plus plus, which is an algorithm which evenly distributes the cluster centers in your input data set. The use mini batch that is set to true and the mini batch steps per iteration indicates that the data is fed into this k-means clustering algorithm in batches. Now that the clusters have been generated, we can use this model for prediction. We'll predict which particular cluster this point belongs to. This point is at 1700, 1700. You should be intimately familiar with estimators by now. Call k-means estimator.predict to run predict on your input data. Make sure your input function takes in our 1700, 1700 data point. And you can see that this belongs to the cluster at index 1. The cluster at index 1 is the cluster in the center. Training initial clusters parameter indicates how the reference vectors for the underlying data were initialized. There are several different ways in which this can be done in the TensorFlow library. One is the reference vectors are set up at random. The second is you can specify an array with specific data points that you want to use as the cluster centers, or you could use some kind of function to generate the cluster centers. Another choice is to use the k-means plus plus algorithm, which randomly distributes the cluster centers across the data.